Thanks, Michelle. Hello, everybody. It's my great honor to introduce Dr. Nicholas Lin today as our first keynote speaker. So Dr. Lin is an associate professor at the University of Cambridge, where he leads the machine learning systems lab and a director at the Samsung AI Center in Cambridge. Prior to joining Cambridge, Dr. Lin was an associate professor at the University of Oxford and a senior lecturer at the University College London. Nicholas also has more than 10 years of experience in industrial research. Previously, he has been a principal scientist at Nokia Biolabs and a lead researcher at Microsoft Research in Beijing. Okay, Dr. Nicholas, the stage is all yours. I would like you to share your slides for today.
Thank you so much for the kind introduction, and it's wonderful to be here. Let me just, quickly share my slides, and we can begin. Does that look fine to everyone?
Yes. I see your slide.
Fantastic. Great, let me start there. Okay, so it's asking to start your video. Hello. It's asking me to start a video. I guess later. Can everyone still hear me?
Yeah, I can hear you.
Okay, great. Okay. Great. So thank you for the invitation. I'm going to focus on a particular part of edge computing today. It's something I've become very passionate about in the past year and a half, and it's an area called federated learning. And in particular, I want to talk to you about work we've been doing here at Cambridge that we're doing specifically to increase the adoption of this really powerful type of edge computing. And in particular, how this relates to increasing the adoption and how teaching can be a major role in this. So this talk will have three main parts. I want to explain why I think federated learning is such an important facet of machine learning moving forward. I want to explain that sort of motivation. And in support of this, I want to tell you about a framework, a software framework that we call Flower. Flower is this vehicle that we're using to allow not just big corporations to engage in this effort of federated learning, but allowing individual researchers and small organizations to fully participate within what we think is a really revolutionary type of advance in this particular era of machine learning. And finally, most recently, I've become aware of the importance of federated learning as it pertains to education. And that is because not only is it difficult for people to adopt this technology and explore it, but we also need to be able to make it far more accessible to students so they can understand federated learning, how have a hands-on sort of awareness of how these how this type of machine learning can be explored and developed. And so we've been doing a lot of work in Cambridge and in a new external to Cambridge organization called the Cambridge AI Academy, where we offer avenues for studying federated learning and other types of machine learning towards this. So that is what I want to focus on today. Let's begin with the main issue, which is what is federated learning and why am I so passionate about it? And to sort of answer that question, I think we need to take a step back and consider what is the de facto way that we interact with machine learning today. And that is through the data center. It doesn't matter what you do in your daily life almost. If you are browsing the web, if you're using your phone, if you're using, say, an Alexa or even browsing on Netflix, all of those experiences that consumers engage in are actually serviced through a machine learning data center. And so this brings along with it a lot of negative externalities that I wanted to discuss with you. And so my thesis is that if we fast forward 5 or maybe 10 years from now, and we look back at this approach to machine learning, which is very centralized, it forces it within the hands of large organizations, and it also forces sort of a paradigm of using static data sets that can be, for example, biased and not representative of the entire distribution reality. It has a lot of negative elements to it. And so my hypothesis is that when we look back at this current state of affairs, we will see strong parallels with it, with a lot of other types of behaviors that throughout history we decided, I get this pop-up, that we decided throughout history were essentially bad ideas that we pivoted away from. So examples of this would be smoking. I want to argue that the use of data centers and centralized learning is analogous to how smoking was not so long ago. It was a popular activity. It was even encouraged by doctors, and these are actually real advertisements that you saw appearing in articles encouraging people to smoke. The same thing happens today. Data centers are completely the de facto approach to machine learning right now. Another analogous situation is that of lead paint. So we thought nothing of painting the interior of our homes with a particular type of paint containing lead, and thought nothing of the negative health side effects of doing that. And finally, and this unfortunately is a situation that we have yet to correct. But if you look at things like climate change and general pollution due to industrial activity, as shown here, this unfortunately, again, is not something that we've moved away from yet, but of course there's widespread belief that we need to sharply change our behavior as a society. And what I'm saying is that this reliance on the data center and centralized learning in the hands of third parties away from users has similar negative effects that we're going to fully realize as time moves on. And so for that reason, I'd argue that we need to move away from centralized learning to more of an edge compute paradigm. An obvious reason for that is user privacy and control. Under this style of federated learning, the data remains in the hands of the user, and yet the models can still be trained. And because of that, that offers enormous user privacy benefits. But not only that, it makes the devices and services that we build using this form of machine learning far more robust. If you have, for example, in the case of some of the work that I might do at Samsung, we consider how do you invent the next generation of robots or medical devices. Now, if the intelligence of these devices relies solely in the data center, then their effectiveness and even their safety of use is entirely premised on the connectivity to that data center. Furthermore, data centers push us to a paradigm of carefully curated, largely static data sets that can never fully represent the real world. They're going to take time to build, and in that time, the world evolves. They're also naturally going to be biased because there can only be a small sampling of what the world really is like. And that's what a centralized data center style of machine learning prompts. But if we start to move towards a decentralized learning where the data is coming from the edge in a constant stream, we can start to overcome some of these really strong negative issues. And finally, you might have heard of the huge carbon footprint that exists for centralized machine learning. So there are studies out there that show, for example, that a SOTA NLP model takes as much as the entire, it produces the same amount of carbon as 5 cars used for the entirety of their life. And so, and that's to train just a single state-of-the-art model. And as models get larger and larger and they consume more and more electricity, this problem is not going away. And so decentralized learning offers, as I mentioned in this talk, potential for mitigating some of these issues. Now, the natural question would be, so what should replace it? I've of course been talking about federated learning so far, but there are other options. So my group pioneered a lot of the some of the more interesting techniques out there for allowing models to be compressed and run entirely locally. But of course, that has this limitation that not all machine learning can be squeezed completely onto the device, and that these type of techniques do not allow the models to learn only before the formal inference stage. There are obviously other types of learning paradigms out there, such as zero-shot learning and so forth, but many of these techniques are not really ready for prime time yet because they can't afford us the types of accuracies that we need for commercial scale services. And so that really leaves us with one option, which is federated learning, which is shown already to be viable in many use cases, and in fact is used by some of the largest companies in the world, such as Google and Apple, for select cases. And so let's now consider what federated learning is in a little bit more detail, just to provide more context to this. And so federated learning is this act of training a machine learning model where the individual pieces of data that go into the training process come from the edge devices. And during the training process, the data can remain with the user on the device, never having to be transmitted to a central source. And essentially, local training is performed on a thin, small part of the data that the device has access to. And these small pieces of information are sent to the server. These are not the data, but gradients calculated against the data. These gradients are then aggregated into a single model update, applied to a model, and then that model is pushed down. And that's how federated learning can function, and is able to generate models that are nearly as good as centralized solutions, but whereas the user or the organization can know that the data never left the device or the institution. And so this is important for enabling many applications. A lot of the ones that we might talk about here, because there's a talk about edge computing, you could think of as being device-centric or robotic-centric. So you can imagine robot perception being trained from data on the edge in a privacy-preserving manner. Already today, we have things like the Google keyboard that are being trained on user data that potentially is very sensitive. But in this case, the sensitive text that people may use and never leave the device, that's also pivotal as a technology to enable things like hospitals or legal entities, government organizations to cooperate, but never actually share the data between each other. And this can actually be necessary not only for protection of privacy, but even for adhering to legal requirements. So for example, in the UK, we have GDPR, which prohibits the sharing of certain types of data. Now, federated learning can allow these things to be possible and still allow those laws to be met, but the learning operations still to be possible. So let me now pivot in the rest of this talk, the rest of the around 10 minutes of the talk, to tell you about what are we doing about the solution to enable what I've argued here is an important innovation in machine learning to increase in its adoption and spread far more evenly throughout the community in terms of users, of researchers, not only just big corporations, but individual people being able to start to use it. And so there are two things I want to talk about. The first of these is a framework we've developed called Flower. Now, I'm going to tell you about the Flower framework very briefly and tell you about a case study and carbon footprint analysis that we've done using Flower. But what Flower is a open source, completely open source, community-driven effort to build software that enables small organizations or individuals to study federated learning at far higher levels of fidelity that would otherwise be possible. And although it's a really recent framework, it's already starting to rival some of the more well-known ones, such as TensorFlow Federated. And although it offers, orthogonal types of capabilities, so TFF or other solutions like PySift, they're great at certain types of facilities, but what we aim for in Flower is this ability for a user with a couple of GPUs to be able to simulate at scale and with high levels of fidelity true federated systems, so they can either explore them or develop new algorithms within this space. Now for technical details, please consult our archive papers, but what I want to do is just get across to you the challenge that exists. So this is a figure that just considers just the scale of different federated systems that exist in papers. X-axis is the number of clients in these papers. Y-axis is the concurrent clients, and each dot is a different paper. And these are high-profile papers in the academic literature. But what you notice is that the scale of these deployments and studies are relatively small if you consider that the actual main objective is federated systems containing hundreds of thousands or perhaps even millions of clients. And so what Flower enables us to do is perform experiments at the far right, far top part of this figure in green. This green dot represents the Flower types of scale it's able to offer users wanting to explore this technology. And you'll see that it's far beyond the scale offered in other types of frameworks that these papers are using. It's not only a question of scale, but it's a question of other forms of realism that Flower enables to be possible, such as compute heterogeneity between nodes or the communication overhead that exists. And so I'm not going to run through all the details of the framework, but I just want to cherry pick and highlight that there's a couple of key technologies inside the Flower framework. One is the virtual client engine. The other is the edge client engine. And it's through these facilities that we're able to let someone explore federated learning under these types of settings, including other types of realism. Flower also allows somebody to, again, with a small amount of resources, so a couple of GPUs, they can immediately start to do these experiments. And normally these are out of reach for everyday students and scientists. This is normally the avenue of large corporations such as Google and Apple and the likes of that kind. But we are enabling it to be done in a way within a couple of lines of code. Somebody can take an existing machine learning pipeline and start to explore how well a federated system could run. Now I want to just quickly show you one result here. Just pay attention to the result on the left-hand side. This is really interesting because it shows perhaps a world's first result where we're using only two standard GPUs and a desktop using the Flower framework and showing it could actually simulate true federated systems up to, in this particular scale, 15 million clients. There's different configurations. That's what the color of lines shows, but it's showing us that the system is able to scale with this modest amount of compute resources under someone's desk. Simulations that are far more representative of what you would imagine would happen in a real deployment. Now I just quickly run through the figures on the right. You can see that essentially this is a trade-off of different other frameworks. And so as we move through different frameworks, of which there are quite a few, in each case, Flower is able to offer far faster training times for the same level of resources. Now, let me just quickly tell you about an interesting case study that we use. So Flower enables scale and exploration. And as a case study, we applied it to this question of, well, what is the carbon footprint of federated learning? It's never been asked before. So we invented a methodology that allowed us to answer this question. You can find the details in these papers. Let me just go through and show you the methodology. So the methodology is one where we developed a carbon footprint model based on the location of devices that accounts for the differences in federated learning versus data center learning. The large fraction of this is to do with the lack of the need to cool. Now, when you have a concentration of GPUs in a single data center, because of sort of thermodynamics, you need to cool them. But under a distributed setting where these devices are physically disparate, no longer need to cool. And so we account for that in our carbon footprint model. It allows us to compare data centers to federated systems for the very first time. We also can consider the location coarsely where they happen to be. And what we found was very interesting. So let me just show you this one result. This is of if you're trying to train a vision model under both centralized and federated settings. And what we found is that for training, for example, a ResNet model to the accuracy of 60%, federated learning solution could be as much as 1.7 times less carbon emitting. And the reason for that is that although federated learning takes longer to learn in terms of the number of epochs, its gradient in terms of the carbon emissions per epoch is far less, and that's what's being shown on this right-hand figure with the red versus blue curve comparison, where red is the data center and blue is the federated learning analysis. And so this is really interesting results because it starts to indicate that with this type of guidance, we could start to understand when should we be using, for example, federated, and when should we be using other centralized solutions if we care about the carbon emissions of this particular task. So this is really valuable methodology that we've built on top of Flower. And then just to conclude, I just want to mention my most recent passion project that is also moving towards enabling rapid adoption and exploration of federated learning, but from a completely different angle. And this is from the angle of how can we get it in the hands of students who are completely new to the machine learning field. And so I've started this work in Cambridge within a few courses I've launched, and we've now looked to another avenue from which we could offer similar material through lecturers, not only from Cambridge, but from other universities, called the Cambridge AI Academy. Let me just run through this very quickly. The key idea as it pertains to this particular topic of federated learning is that most of the type of content you see in this space focuses on slides, like you see on this left. What we've been able to do is use Flower and embed it inside Google Colab to sort of complement theoretical teachings from slides to hands-on teaching with a very rich and powerful federated system. So the student can really understand all the detailed nuances of it. And then hopefully they can start to come up with their own brand new ideas about how we can start to do federated in a more efficient and accurate manner. So the aim here is to allow immediate access to any of the Google Colab sort of a viable browser to be able to have experiences of this hands-on nature that can really complement the usually more theoretical grounding of this type of teaching. And so we've seen that in Cambridge, this has worked really effectively. And so this is a news article that we had last year when we launched this for our students there. You're welcome to read the article. But then what we've done after that is said, well, how do we get it beyond just Cambridge students? And so then talking to a number of colleagues at different universities throughout Europe, around 8 of us have got together and we've come up with sort of an ensemble of teaching that's done on a complete individual basis. So it's not related to Cambridge as a university, but there's folks from Edinburgh, Cambridge, Warwick, other places in Europe, where we're offering courses that are built in this manner, where we're trying to, in this case of federated learning, but on other topics, allow students to immediately get a hands-on view on really technical areas that are emerging, like federated learning, but also other types of machine learning system topics, and so on. And I believe Philip and Fiona are going to talk about this in a couple of hours if you're interested. Now, I know there's some questions, so I just wanted to give you one sort of like food for thought, and that is that if we invest heavily in federated learning and we get a lot of adoption, we can bring students on early on to study these core challenges that we need to overcome. I think there can be a future for learning where we pivot away from data centers that are currently the dominant paradigm for many consumer situations and move to one that is dominated by federated systems, where the data comes in from the edge, it's already in domain, it's already adapting to class drift and concept drifts. And so then it offers not only a more private, a more distributed, a more fair solution that's in the hands of users, but it's also more accurate. And that would be a complete shift in the paradigm we see today, but I think it's on the horizon, perhaps as soon as 5 years from now. So with that, I am happy to take questions and any ideas, or if you're interested in participating, just drop me an email and we can talk further. So thank you again for this opportunity to talk today.
Thank you, Professor Nick. So wonderful presentation. Let me see if you can start your video so that everybody can see you. That will be perfect. Yep.
Oh, sure.
I myself is a hardware engineer. I don't have a lot of experience in this federated learning area, but I do collected many questions from the audience. The first one
Sure.
is, what are some regulations and the laws in place to protect user privacy and the data ownership when users contribute their devices to participate in edge computing?
Oh, well, so if you can engineer these systems such that the user data can be heavily protected. So there are methods such as secure aggregation and differential privacy. So users can have strong protections about their privacy. Fundamentally, the raw data is never leaving the device. So there's always that protection, but there can be second order kind of concerns to do with the sharing of gradients and so on. But those issues can also be protected through security means. They have to be kind of carefully engineered, but for many applications, they can be done well.
Got it. The second question is, what do I need to start using Flower?
You can visit flower.dev and just pip install. And if you've got an existing training pipeline that you've written in PyTorch or TensorFlow, within 2 or 3 lines, you can federate it. And then most of the effort I was talking about today was saying, how can we let someone then take that and scale it to a scale that makes sense for analyzing in a federated setting? Because these things are never just 1 or 2 nodes. They're always in the scale of, dozens, hundreds, or much more.
Got it. The next question is, where can I learn more about federated learning?
Oh, so there was a fantastic tutorial at NeurIPS last year. If you there's good content from Google if you want to just run through some regular stuff. I guess at the academy that I mentioned, if you want to take an actual course from a faculty member, you could use some of these Google Colabs that we've built up, if that was the kind of what they're asking. But if you just want to kind of look at some of the academic material, I think just the tutorial from NeurIPS is probably the best one, but it lacks the hands-on component. TensorFlow Federated has some pretty good examples you could run through too.
I think we still have time for another question. Is what do you think are some of the strategies that can help speed up the commercialization or monetization of the edge computing technology?
Oh, I see. Yes. Well, so really, I think the key is accessibility in terms of software frameworks that make it easy. So perhaps something that I didn't quite articulate was that what federated learning really lacks today is the type of framework support that we enjoy for conventional learning. So, PyTorch and TensorFlow do a great job of letting anyone jump into this area and do some centralized training at a level of sophistication that is, quite comparable, quite analogous to even large organizations. They use the same tools essentially. But in the world of federated learning, those tools don't really exist today. And so we hope that Flower can fill that void. And there are other frameworks too that are trying to fill this other dimensions of this void. But I think one of the big obstacles right now is frameworks that allow people to get started and either develop an application or explore the area towards solving one of the open problems. That's the key problem in my mind. The more people we have working at a high level in the space, the faster it'll move.
Got it. Okay, I think that's the time we can conclude for today's section. Again, thank you very much, Dr. Nicholas, for this wonderful topic in the federated learning and edge computing. I know it's pretty late. It's already 1:40 in the morning.
Yeah, it's 1:40 exactly. But I'm really happy to have the chance to speak to you all today, and thank you for the invitation.
Sounds great, and we hope you have a wonderful night.
Okay, take care.
Thank you. Bye-bye.